NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams.
Pluto, the confounding little planet residing at the outer extents of our nearby planetary system, is stirring up excitement within the cosmic community. Continuous reports indicate a possible encounter with Neptune, raising concerns among scientists and space enthusiasts alike. Esteemed experts, including Neil deGrasse Tyson and Michio Kaku, have sounded alarms about the potential consequences of this celestial conflict. But how did Pluto end up on a collision course with its distant neighbor? And how might this cosmic event affect us here on Earth? Let us examine this unfolding situation. Once thought to be an irrefutable planet, Pluto was subsequently reclassified as a dwarf planet due to its unusual orbit. Regardless of this change, it continues to captivate and attract space experts. Ongoing predictions from prominent scientists highlight a concerning proximity between Pluto's orbit and that of Neptune. These experts warn against a potential impact between the two planets, posing a significant threat to Earth. Pluto's journey around the Sun is marked by its extraordinary characteristics within our nearby planetary system. Its orbit spans an astonishing 248 years, and since its discovery in 1930, Pluto still hasn't completed a full revolution, adding to its intrigue. The notably eccentric shape of its orbit deviates from the nearly circular paths of the major planets. Additionally, Pluto's orbit is tilted at 17 degrees to the ecliptic plane, making its trajectory more extreme compared to other planets. One remarkable feature of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, defying expectations based on their relative positions in the solar system. So why hasn't a collision occurred between Pluto and Neptune? The explanation lies in the gravitational forces exerted by other planets. The analysis of Pluto's orbit began soon after its discovery, presenting a unique challenge for astronomers. Unlike most planets, whose orbits align relatively close to the ecliptic plane, Pluto's distinct characteristics include a steep inclination and an eccentric orbit. The mystery deepened with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit amid these complexities serves as evidence of the intricate dynamics inherent in celestial mechanics. The three-body problem in space, which involves calculating the motion and gravitational interactions among three celestial bodies, e.g., Pluto, Neptune, and the Sun, explains the complex interplay of their paths and gravitational forces. Terms like libration and the Kozai mechanism help unravel this celestial mystery. Astrophysicists argue that libration, responsible for maintaining planets in their orbits, plays a key role in the Pluto-Neptune system. This phenomenon ensures that when Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune, effectively preventing potential collisions. Libration ensures that when Pluto approaches Neptune or other giant planets, it is predominantly arranged above their orbital plane, adding an extra layer of safety against impacts. The Kozai mechanism explains why Pluto's orbit around the Sun appears irregular yet remains stable over time. Despite apparent randomness, numerical simulations in the late 1980s revealed that Pluto's orbit, though seemingly chaotic, maintains long-term stability. Small initial deviations can lead to significant changes over millions of years. However, Pluto's unique orbit remains stable over extraordinarily long timescales, keeping disruptions within limits. Ongoing computer simulations have enhanced our understanding of how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune's unique relationship with Pluto, completing 3 orbits for every 2 of Pluto, contributes to the stability of Pluto's orbit. Furthermore, Jupiter's massive gravity exerts a significant influence, while Saturn's effect, though smaller, also plays a role. Through extensive studies, researchers have shown that the combined effects of Neptune, Jupiter, and Saturn ensure the safe and stable movement of Pluto in space for billions of years. These phenomena are crucial for maintaining the order and stability of celestial dynamics in the universe. Without these mechanisms, the solar system would be prone to greater chaos, potentially leading to impacts or ejections from stable orbits and causing widespread implications for other celestial bodies. Understanding Pluto's orbit is particularly important in discussions about a potential collision with Neptune in the future. This knowledge provides clearer insight into the dynamic nature of the planetary system. Pluto's case highlights how seemingly unstable orbits can achieve equilibrium through the complex interaction of gravitational forces and orbital mechanics. Continuous observation and study of these phenomena are essential for gaining a deeper understanding of our place in the universe. Exploring the depths of space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit serves as a perfect example of this unpredictability. The concept of orbital chaos vividly demonstrates the delicate dependence of a celestial body's path on its initial conditions. As illustrated in Pluto's case, even slight variations in the dwarf planet's position or velocity can significantly alter its long-term orbit. Computer simulations have been instrumental in helping scientists understand how Pluto moves in space. By making small adjustments to these simulations, space experts can observe how even minor changes can greatly impact Pluto's trajectory. In the late 1980s, these simulations uncovered a fascinating aspect of Pluto's orbit. Despite factors like libration and the Kozai mechanism contributing to its stability, Pluto's orbit can still exhibit irregularity. Even a tiny initial difference in Pluto's position or speed can lead to major changes in its orbit over many years. Despite this inherent chaos, Pluto's orbit remains stable for an exceptionally long time, spanning billions of years. This suggests that beneath its seemingly unpredictable appearance, Pluto's journey around the Sun follows an underlying order. Predicting celestial events and the future paths of heavenly bodies, especially with planets like Pluto that have unusual orbits, is extremely challenging. The inherent unpredictability of these systems makes long-term forecasts uncertain. Mathematical simulations help us understand and predict the future movements of celestial bodies, but they also reveal the limitations of our predictive capabilities. These models heavily rely on precise initial conditions and simulate complex interactions. Even a small error can lead to drastically different outcomes, making accurate predictions difficult. The chaotic nature of celestial orbits, such as Pluto's, reminds us of the ever-changing universe. While we've made progress in understanding space, the cosmos continues to be a realm of mystery and awe. Pluto's case features our continuous restricted information. Understanding the gravitational effects of monster planets on Pluto's circle gives important insights into the broader dynamics of the solar system. It shows how the presence and position of every planet can influence the stability and course of other bodies in the system. Disregarding these intricate forces, prominent astrophysicists are expressing concerns about a potential impact between Pluto and Neptune. Neil deGrasse Tyson, a renowned astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly regarding Pluto. Tyson, famous for reclassifying Pluto as a dwarf planet instead of a full-fledged planet, shares insightful thoughts on how our understanding of celestial mechanics is constantly evolving. Tyson views Pluto's reclassification not as a demotion but rather as a necessary adjustment to our growing knowledge of the diverse objects orbiting the Sun. His approach to celestial mechanics involves continuous learning and adaptation. Tyson sees the complexities of orbits like Pluto's as evidence of how much more there is to discover in space. He believes that the allure of these mysteries makes astronomy so captivating. Furthermore, Tyson is aware of how space-related events and discoveries capture the public's attention. He sees events like Pluto's reclassification and its peculiar orbit as opportunities to engage the public's imagination and curiosity about the universe. By discussing the dynamic and sometimes unpredictable aspects of space mechanics, Tyson encourages a deeper understanding and enthusiasm for the cosmos. Neil deGrasse Tyson opens a window for the general public to marvel at the wonders and mysteries of the universe. Working alongside other experts, Tyson actively warns the public about the potential risks of Pluto's unusual orbit. After extensive research on Pluto, he has raised concerns that the three-body problem could pose a serious threat, suggesting that a collision with Neptune might be long overdue. Moreover, Tyson emphasizes how such a collision could disrupt the balance of the solar system, potentially leading to catastrophic consequences extending even to Earth. An impact between Pluto and Neptune would be an extraordinary and disastrous event in our solar system. This collision would release an immense amount of energy, likely disintegrating Pluto due to its smaller size and icy composition. Debris from the collision could spread throughout the solar system, posing potential dangers to other planets and their moons. For Neptune, such an impact could potentially alter its atmosphere and orbit, depending on the specifics of the collision. Michio Kaku, a famous theoretical physicist known for his work in string theory and science communication, offers an interesting perspective on this scenario. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics provide profound insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital mechanics of celestial bodies like Pluto, according to Kaku, can offer crucial insights for future space missions. This knowledge can help in navigating the solar system more effectively, anticipating potential risks, and planning missions to the outer reaches of our planetary system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a framework for approaching and understanding distant worlds. In discussing the physics of planets, Kaku often highlights the significant connection between celestial mechanics and theoretical physics. He believes that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated events but are tied to fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, aims to grasp these principles at the most fundamental level. He suggests that studying the complexities of celestial mechanics, like Pluto's orbit, can yield insights into the fundamental laws of the universe. Like Tyson, Kaku has also addressed the potential collision, relating it to his theories about the universe. If Pluto and Neptune were to collide, it would be a monumental event in cosmology, providing a unique observational opportunity that could potentially contribute to our understanding of string theory. String theory, a theoretical framework that replaces point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. The impact of such magnitude in the solar system could create extreme conditions of energy and gravity, offering insights into the behavior of fundamental particles and forces under such conditions, a significant focus in string theory. Additionally, the gravitational waves produced by the impact could provide valuable data for testing predictions of string theory related to gravity and spacetime. While the direct impact on Earth would be minimal due to our distance from the outer solar system, the scientific implications of such an event could be immense, potentially advancing our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit serves as a key example of celestial mechanics, demonstrating both stability and chaos within our solar system. The extraordinary dynamics of its orbit, influenced by the gravitational forces of neighboring planets, especially Neptune, highlight the complex and dynamic nature of space. The universe holds countless mysteries, and the three-body problem is just one of them. There are other potential disasters that scientists anticipate. While the chances of planets colliding in space are very low, it is not entirely impossible. The way planets' orbits are influenced by various factors, including gravitational interactions, is explained by the three-body problem. In some systems like TRAPPIST-1 with 7 Earth-sized planets, gravitational forces create a rhythmic pattern called orbital resonances. Over time, these patterns can make planetary paths less stable, potentially leading to collisions. Despite the crowded nature of systems like TRAPPIST-1, collisions are not currently occurring. Researchers closely monitor these systems to understand how planets affect each other's paths, particularly when they are close to one another. This information helps us understand the evolution of planets in space. Rogue planets drifting through space without orbiting a star present an additional curious element. These planets, once part of a star system, are ejected due to gravitational disturbances or other cosmic events. For example, The close approach of another star or dynamic instability in other systems can cause these rogue planets to travel vast distances, potentially reaching areas far removed from their origin. During their solitary journey, there is a possibility of them encountering another star system. If one of these rogue planets enters another nearby planetary system, there is a slight chance of a collision with a planet in that system. However, given the vast and mostly empty nature of space, the likelihood of a rogue planet directly impacting another planet is extremely low. The immensity of interstellar distances and the rarity of planets in open space serve as barriers against frequent collisions. Moreover, rogue planets are relatively rare compared to the number of stars and planets in stable orbits, making such encounters even more unlikely.